Hello, welcome to our presentation entitled Coherent Optical Wireless System for Next Generation Home and Corporate Networks. This is the presentation for the project website. The project has the same name. My name is Thomas Kamalakis. I am an assistant professor at Harokopio University of Athens. In this presentation, we aim to give some bibliographical data for the optical wireless technology, the coherent optical wireless technology, and focus on some of the main project findings. Now, the COWS project, as I said, is derived from the full title is Coherent Optical Wireless System for Next Generation Home and Corporate Networks. The acronym is COWS. This is funded by the ARISTEIA ΙΙ action. This is what we call somewhat of a national project. It was filed in the corresponding call of ARISTEIA ΙΙ. ARISTEIA means excellence in Greece. In Greek, sorry. The overall budget, the initial budget was 250 kilo euros, and the duration is 1.5 years, approximately 1.5 years. The project ends at October 2015. Before I start, I would like to say a few things about the project team. It consists of 3 faculty members, including myself. We also have 3 postdocs aiding in this endeavor, and also 4 PhD researchers. Now, before I start discussing the findings of the project, it may be important to go over a few basic stuff about optical wireless technology and its potential applications and application scenarios. Now, what is optical wireless? Optical, we know, is from optical communication. Optical communication systems are all around us, even if we don't usually realize this. They have brought large data rates to the final at the subscriber lines through ADSL. ADSL, of course, is copper-based, but behind the DS lamps, that is behind the ADSL, let's say, central offices, there are fibers connecting these offices with the rest of the carrier infrastructure. So, although we don't see the fiber coming up to our apartment or our building, that doesn't mean that optical fiber does not help us achieve these large data rates that are currently available with ADSL or VDSL. Of course, in many countries, fiber to the home or fiber to the building is already a reality. And for example, in Japan, the subscriber number is for FTTH is much larger than that of ADSL, and there are many countries that are thinking of seriously investing in broadband access technologies based on fiber to the home. Now, okay, we have optical communications, that's one pillar, and we now consider optical wireless. Before I said that optical communication is mainly fiber-based, so what is this stuff about wireless optical? Now, the idea is that for short distances, either in an indoor environment or in an outdoor environment, you could consider transmitting the data directly without any fiber. Let's say that is to say, transmit directly in free space. Now, the basic idea is that you already have some transceivers available that can operate at high data rates. So why not use collimated laser beams, for example, in order to establish an end-to-end connection, a point-to-point, connection, without installing the fiber. Now, this idea is not that new. It has been considered mainly for outdoor links. There are many companies offering commercial products for let's say point-to-point outdoor communications. Such systems are typically used to connect campus buildings in universities or company buildings inside the company campus and stuff like that. These systems have been around for nearly a decade. They are mainly based on intensity modulation direct detection. That is, if you use a laser to transmit the data on free space, then you only change the intensity of the laser beam. You don't try to change the phase of the beam, and this is a fundamental property of many optical communication link, either wireline or wireless, and it is mainly done because of the simplicity of the implementation. Now, the other thing is that you usually select a wavelength around 780 nanometers or 800 nanometers. This is usually the wavelength of choice. This is mainly because of cost implications. That is, you can have much cheaper laser diodes operating at this wavelength. And up to now, there are many commercial solutions achieving 1 gigabit per second connectivity over a distance of 1 kilometer or even larger distances. Now, of course, this is let's say the most mature commercial application. If you talk to the vendors, they will say that this system has a lifespan of more than 10 years, and it's much more suitable to install such a system instead of installing connecting the buildings or what have you with fibers, because the fiber is usually installed underground, and this means that you have a large cost associated with fiber installation and public works and stuff like that. And of course, you need to obtain the proper license depending on the law of each country. From my experience, when we needed to install a small fiber network inside our university, the actual road work and the fiber installation took 1 week to complete and test, but the bureaucracy and the applications you need to file at the ministry or the other authorities took about 2 months. And this is probably the best case scenario that we encountered. So anyway, these systems are already being installed. There are, of course, some indications that this technology could also be used for satellite links, because there is currently much debate about how the satellite networks can sustain high data rates using just microwave links. And from my point of view, this is rather difficult, so you need to consider such technologies for satellite-to-satellite links. There are even some indications that this technology could be used for ground-to-satellite links. Of course, the atmosphere over such long distances between the ground and the satellite can be quite troublesome, medium. For the short-range links, the terrestrial links I spoke before, usually the atmosphere is not such a very important, it does not pose significant impairments. The main impairment is, of course, fog, because when fog falls, the visibility is decreased. This means that the attenuation of the optical beam is very high. There are some cases, I believe, that in Austria or Germany, that they measured attenuations up to 300 dB per kilometer. This is quite large attenuation, and of course it is very difficult to sustain communication over such distances. So probably the most important impairment for such an outdoor link is the weather conditions, and especially fog. These systems are not mainly influenced by fog, and much less by rain or other effects such as snow and stuff like that, the wind. And here you see an actual free space optical link, one side of course. This is a free space transceiver, the back of it. It kind of looks like a camera. Here there are all the necessary optics and transceiver electronics and stuff like that. This was set some years ago. I believe this is the University of Athens. We have installed, when I was in the University of Athens about a decade before, we have installed such a system in order to measure its availability, that is how much time it can remain alive and not be interrupted by the weather and stuff. It had an excellent availability. I believe it was 5 nines. 5 nines means 99.999%. It was 99.999% available. That is, there was only a small fraction of its operation time. Its operation time was about 6. We measured it for about 6 months, and it had a very high availability. Now, usually, if you want this high availability to be guaranteed, you also need to install a microwave link. It's also not, although it's not directly related to our presentation, it may be interesting to say that this microwave length operated in the millimeter wave range, and it was kind of a complementary backup, let's say, link. Now the free space optics system operated at 1 gigabit per second. This was a rather high, I would say, record-breaking data rate for such a commercial system. The microwave backup was the millimeter wave backup was at 100 megabit per second. Now, it has long been considered that long been suggested that optical wireless could also be used in the indoor environment. Now, the first, I believe, paper discussing this approach dates back to 1979, in the that is the early 80s, the late 70s, sorry. Now, at Stanford University, by the mid-90s, the group by Professor Khan and associate had demonstrated an optical wireless prototype able of transmitting 50 megabit per second using high-powered lasers. This was a very important and demonstrator for that time, and but today, some 15 years later, there are some laboratory demonstrations achieving 10 gigabit per second in an indoor environment. But these, of course, are not commercial systems. These are tested inside the laboratory. Now, why do we need to consider the indoor optical wireless as a solution? First of all, besides the large data rates, 10 gigabit per second is a very large data rate that cannot be achieved by conventional wireless technologies, even at short range. I mean, Wi-Fi can only, at best, can achieve 600 megabit per second, and this is quite an optimistic data rate. From my experience, it can never achieve an effective data rate of 600 megabit per second. Okay, so besides the large data rate, what other advantages, what are the pros of this technology? First of all, there are no license fees. Okay, this is exactly like Wi-Fi. No one pays a license to a proper government authority to use the Wi-Fi band. And okay, so this is exactly like Wi-Fi, or similar to Wi-Fi anyway. There are no biological concerns. I mean, the public should be much less worried about infrared or visible light communications, because we have already been exposed to a large amount of infrared radiation because of the sun, and we survive. So there are reasons to believe that the biological implications of using this technology will be much smaller than, say, radio or microwave bands, where we actually don't know. Don't know for certainty what is the biological implications at these bands. Of course, there is another another pro for using the indoor optical wireless system, that there is no interference with legacy RF radio frequency systems. If you already have a network, a Wi-Fi network, and you want to install an infrared network, there will be no interference. Okay, there are excellent transceivers already available from the fiber cousin, from fiber optic communication systems. The laser beams are rather difficult to eavesdrop, since the beams are confined by the room walls. That is, outside your house, one could pick your Wi-Fi signal and eavesdrop it, or use it for his own purposes. This is very difficult for when optical wireless is as far as optical wireless is concerned, because it is not easy it's impossible rather for the optical beams to leave the confines of the room. And another interesting advantage of the optical wireless approach is that it can be combined with illumination, and there is a lot of stuff and a lot of research now towards this direction. This is a very interesting idea. We are already considering light emitting diodes, white light emitting diodes, for providing next generation illumination systems. So the LED, the white LED, is not very bad itself. It's not very bad for communication purposes. Okay, granted, it has a limited modulation bandwidth. It has some problems, but the mere possibility that you could use the same LED to provide both illumination and data communication is very attractive. You see here a prototype system. This was developed by Siemens in the ICT project Omega in 2010. We have this demonstrator at our lab, and we did some very interesting measurements on this. I believe the record for such a system, for data communication with such a system, is about 2 or 3 gigabit per second. So it has a lot of potential. Of course, there is the question of which distance can it cover and stuff like that. It can typically operate in a typical indoor distance, 2 or 3 meters high. Now, okay, these are the pros of the technology. What are the cons? What problem does the optical wireless technology pose? Now, I have talked about this earlier. One problem is that you can only use intensity modulation. Intensity modulation is fine for low data rates. It has a small implementation cost, but as you increase as you are required to transmit data at higher data rates, the bandwidth requirements of intensity modulation become not only the bandwidth and the power requirements of intensity modulation become quite high, and this means that you cannot easily satisfy high data rates with conventional electronics. You need, let's say, you need transceiver amplifier, electronic amplifiers with a large bandwidth. Now, as you also need higher power, higher optical power, you need to transmit stronger laser beams in the air. You get higher cost because high power laser diodes are not very cheap, and you also come across the eye safety restrictions. Ideally, you would like your product or your transceiver to be Class A. That is, you would like to look at it, to be able to look at the laser beam directly without losing your eyesight. Of course, there are many I'm not sure you would risk looking at a Class A product laser diode directly. But anyway, imagine if you are not even compliant with this Class A specification. Systems could be considered dangerous for operating in an indoor environment. Now, another drawback of indoor optical wireless is that you have, much like the radio systems, you have multipath propagation. That is, you run the risk of the connection between the transmitter and the receiver. There may be the direct path connecting the transmitter with the receiver, but there may be an indirect path where the beam, the optical power, an amount of optical power could reach due to secondary reflections at the surfaces of the room. And of course, there are ways to mitigate this in radio systems as well. This causes what we call inter-symbol interference. And there are ways to mitigate this, but as the data rates are increased, the electronics required to mitigate this also become more expensive, because they should work at higher speeds. And all of these drawbacks, all of these considerations typically increase the cost of the implementation, and this is a reason why we haven't seen any, I shouldn't say any, but we haven't seen a broad commercialization of this technology. Now, why do we need to consider coherent detection? As I said previously, most indoor optical wireless systems are IMDD, intensity modulation direct detection. This is rather easy to implement, but why in the CAUS project did we consider coherent detection? Now, coherent optical communication is not something new. It has been considered as early as in the 1980s. There was a growing interest for coherent systems. They have there are two. I believe there are. Okay, what is coherent communication? Coherent optical communications. You mix the incoming beam with a local oscillator beam at the receiver, and this mixing produces a gain, because what you actually do is you mix a weak the weak receiving signal with a strong local oscillator signal, local oscillator field rather. So due to this mixing, you get an equivalent gain. It translates to your signal appears amplified at the receiver. Sorry. So what are the advantages of coherent detection? It has, besides this inherent gain, which means lower power requirements at the transmitter side, there are 4 other advantages. You have high spectral efficiency. It has been shown that coherent optical communication can use both amplitude and phase modulation formats. Phase modulation formats are much more power and spectral efficient. There is the idea that you can use coherent detection to sense only a wavelength, a specific wavelength. That is, if you consider that you can have many wavelengths, a transmitter that transmits many wavelengths. The fact that you mix the incoming signal with another, with the local oscillator signal, this mixing is best when the wavelengths of the incoming and the local oscillator fields match. So this is a way to carry out a precise wavelength demultiplexing. Okay, and we will discuss that in coherent optical communication you have no multipath effects, because when the incoming radiation from secondary paths reaches the coherent transceiver, you have it cannot mix with the well organized and coherent local oscillator laser beam. We will discuss this later. And the cons, what are the disadvantages of the coherent technology is the need for carrier recovery. That is, to obtain a sufficiently good mixing and a high gain, you need the phase of the signal and the phase of the local oscillator to be very well matched. There are ways to achieve this, as we will demonstrate shortly. So this is the first part of our presentation. I would like to thank you for your attention and hope to see you. Hope you will follow the second part of the demonstration. Thank you very much.